All right, good afternoon, everyone. Welcome to session number 5. In this session, we'll have 4 more presenters during this time. Our first presenter will be Kathleen Weichman from University of California, San Diego. Her field is laser plasma physics, and her advisor is radiography. And she did her practicum at Los Alamos National Laboratory in 2016. Today, she will be presenting on ion acceleration by relativistic-intensity lasers with magnetized electron focusing.
All right, thank you. So today I'm going to be talking about ion acceleration, and there's a few kind of key words in this title that I'm going to try to explain going forward. But to give you a 10,000-foot overview, my whole talk is about answering the question, what can a magnetic field do for laser-driven ion acceleration? So first off, I want to make sure I give thanks where thanks are due. Big thank you to the CSGF. Thank you all for making it back from lunch. And in particular, there's a few people that I want to make sure I mention. So those of you who know me, who saw me 2 years ago, the last time I was here, may remember that I was a grad student at UT Austin. I transferred to UC San Diego and changed advisors in January. So I have to give a big thank you to Lindsay Iltz for making that a really smooth transition. I know she's probably outside, but someone will hopefully thank her for me. I also want to give a shout out to Arik, who I'm sure has told many of you the story of how he fired his first graduate advisor. He told me I could say that. And for the younger fellows in the audience, I think it's important for you to know that having this fellowship can really enable you to pursue opportunities that might look a little different than the standard picture of one university, one thesis advisor, one dissertation topic, and if you don't like it, you're stuck. Moving on, I want to thank my practicum supervisor, Gianluca Delzano, and my current advisor, Alex Arefiev. So I'm going to start with the first 2 words in my title, ion acceleration. The basic idea of the kind of thing that I'm going to talk about today is you hit a thin, solid target with an intense laser pulse. So in this case, we're shooting thin, 5-micron thick plastic. And I'm going to show you simulations that are done with sort of a short pulse duration in 2D. This is just to illustrate the mechanisms that are involved. What I'm going to talk about today is sort of fairly general, actually, but this just looks clean. And at the end, I'll touch on what happens with a slightly longer pulse duration. The other important part about my work is that it is an intense laser pulse. So there's a few consequences of this. The first one is something that I put in my title, relativistic intensity. This is important because if you have a not very intense laser pulse and you have an electron that's moving in this electromagnetic field, the electron just basically goes up and down at one position. However, when the electron motion can become relativistic, the electron can gain some forward momentum, and it can travel in the forward direction with this laser pulse and maybe even outrun it and go through whatever target you put in front of it. The second consequence of having an intense laser pulse is that realistically, you never shoot a nice thin piece of unionized solid. There's always some pre-pulse associated with a real laser pulse. This arrives before the main pulse. It ionizes things, and this ionized plasma can expand somewhat. So we're always shooting some low-density plasma out in front of our solid target. There's a third consequence of using high-intensity laser pulses, that there is no such thing as a target post-mortem. You open up your vacuum chamber after your experiment. You ask, where is that lovely piece of plastic that I just shot? Well, it's deposited in a thin coating on pretty much everything that's inside that vacuum chamber. So the real trick to my field of laser plasma physics is trying to get something out before everything in your experiment essentially blows up. All right, so now let's go be more specific about this. There are different kinds of ion acceleration. I'm going to be talking about ion acceleration that's driven by hot electrons. I already mentioned that if you have relativistic intensity, you can get forward electron motion. These electrons can then go through the target into what was formerly vacuum. This is charge separation. It's a sheath electric field. The electric field then pulls ions out of the rear side of the target, and these ions are accelerated. So this process, when all the acceleration is normal to the target, is called the uncreative name target normal sheath acceleration. It's a very widely used and robust mechanism. However, it does have some issues. So the one I'm going to focus on today is the issue that as electrons come through this target, they're slowed down by the sheath field in the longitudinal direction, which is, in this case, x, this plane. But they can still spread out along the target surface. And this spread will terminate the ion acceleration. There, however, is another important consequence of this, which is as these electrons come out, they tend to pull the ions, rather than just straight forward, kind of out as well. And this is a problem because you want to actually use these ions for something. You're not just doing ion acceleration for the sake of ion acceleration. In particular, some of the applications of these kinds of ion sources are creating states called warm dense matter, where you're trying to heat things up to conditions that you might see, say, in the core of a planet. Maybe you're trying to deposit energy into an inertial confinement fusion capsule and cause fusion reactions. Or maybe you're trying to image something with protons, or you can also look at strong magnetic fields this way. And for all of these applications, if your ions spread out, that's bad. So the question is, how do we prevent the hot electrons from spreading out? One proposal is to add an externally applied magnetic field. So you can ask, how strong of a field do I need? Is this feasible? Well, you want the hot electrons to undergo gyro motion, i.e. spiraling around the magnetic field lines within the distance scales in this problem, which are microns. This prescribes that you need a kilotesla level static magnetic field. Give you some reference points on that. It's somewhere between an MRI and a neutron star. And yeah, right? Totally doable. And it's maybe a 30th of the magnetic field associated with the laser, but that's an oscillating field. This is a static field, and we have to use special techniques in order to generate it. However, we can actually do this in the lab and really experimentally produce fields that are essentially static and uniform for the purposes of the processes that I am studying. I want to point out that this is sort of a fairly newish development, and really this is an entirely new, mostly unexplored area in laser plasma physics. So I'd be remiss if I didn't say something about the computation. I'm really mostly a physicist, though. But the computational demands is also one of the reasons that this area hasn't been completely explored yet. I do simulations using the open source particle and cell code epoch, and both 2D and 3D. In particular, the 3D can be sort of medium to expensive, maybe 500,000 CPU hours per simulation, upwards of 50,000 CPUs. So these are not small things to do, and I'm always in the quest for getting more CPU hours. And even in my field as a whole, this is one of the big challenges with plasma physics of pretty much any description, is you're always running up against the limits of what you can do computationally. So I'm in the process of getting more hours to do more 3D simulations. That's what everyone wants. So let's go back to the physics aspect and ask, what is the promise of adding this magnetic field? What does this turn out to be in the simulation? So first, here's the case without the field. The black arrows that are sort of hard to see are the electric field vectors. So when I add the magnetic field, these are all on the same scale, by the way. I see that instead of having the hot electrons spread out kind of up and down along the surface of the target, they're really very well confined. That gives me a higher accelerating field. And in addition, if you look way out here, you actually see some electric field that points inward toward the axis. So this is a potentially focusing structure for ions. Now the question is, like, does this actually translate into a very nice ion source? So we have to look at this sort of in two stages. So early in time, you have a bunch of electrons that come through your target. Now you have electrons that see magnetic fields. There's also electric fields associated with the electrons not spreading out a ton. And this gives you different kinds of plasma drifts. One of them is the diamagnetic drift, and this acts to reduce the magnetic field that the electrons see. I'm calling this the diamagnetic bubble. I'm kind of helpfully guide the eye on where the electrons are seeing magnetic field versus not seeing magnetic field. The ions themselves are being pulled out within this bubble. This has consequences. One, even though we do have the confinement of the electrons, especially in this region outside. They are seeing a fairly large accelerating field, larger than the case at 0 Tesla. However, there is an initially defocusing transverse electric field for these ions. So if this were the end of the story, we would be in trouble, because this actually, it turns out, produces a fairly large divergence ion source. However, later in time, these ions can actually, I'm showing protons here, but this is true for carbon as well, they can actually outrun the bubble or escape the bubble. So when this happens, they are no longer really seeing an accelerating field, but they see a field that is focusing to them and pulls them back towards the axis. And it turns out if I run a very long 2D simulation, I actually see these ions form a very nice beam. So this is quite desirable. But the proof is really in the 3D simulation here. Actually, the 3D simulation results look even more drastic than the 2D results in terms of both the proton and the carbon energies being substantially increased. But there's one more important component, which is what is happening to these ions. Are they going towards the axis, or are they going away from the axis? So to address this, I'm going to show you some plots that are energy versus angle. And we do I do particle tracking with this code. So first off, let's ask, here's the spectrum for all of the protons that I have in the problem. Now, let's look at just the protons that are moving away from the axis. So these are the protons that we don't want. In the case where there's no magnetic field, this is basically all of the protons are moving away from the axis. So when we add the magnetic field, if you look at all the protons, you think, OK, there's a similar angular spread to the case where I have no magnetic field. But now let's look at the population that's the ones that are moving away from the axis, the ones we don't want. This is only a small portion of the total number of protons. And in fact, if I look at where these protons are in space, those are the ones that are actually already really close to the axis. So this is an extremely good proton source, and I think this is the signature same signature that I see in 2D that leads to a very nice, beautiful propagating beam of protons with, it should be pointed out, higher energy than when there's no magnetic field. So as one last point, I showed you a lot of simulations that were for short pulse duration. We actually have an experiment coming up in November in Japan to do this magnetized electron sheath acceleration. That experiment's going to use a longer pulse. So I've been looking at modeling this longer pulse duration and what effects that might introduce. It turns out things are a little bit more complicated, and some of this complication introduces an optimum field for the acceleration. So what I mean by that is, as you increase the magnetic field that you put on this simulation, you find a peak in terms of the energy of the protons and the carbon ions that you're accelerating. We don't exactly know where this comes from. Our current investigation is looking into other magnetic fields that arise in this problem and whether these might interfere. We can get magnetic fields that are on the order of twice the initial field that we seed in the simulation, and these could be a problem. Again, this is in progress. So I want to summarize what I've talked about, this mechanism called magnetized electron sheath acceleration, that by adding a magnetic field, you essentially limit the hot electron spread. And this leads to a two-stage process with a diamagnetic bubble. The first stage is acceleration of the ions in the forward direction within the bubble. followed by a second stage that focuses these ions and can potentially form nice ion beams. So the real potential takeaway here is that you can get higher ion energies with lower divergence, maybe even true beams of multiple ion species, and this is the kind of thing that you really would want to use in experiments that use ion sources. However, there are still some details that we're working out, particularly in relation to our upcoming experiments. So with that, I want to say thank you again and take questions.